Good morning, it's Monday. I hope you are all feeling fresh and had a good sleep over the weekend. I have written today's agenda here. The last thing we looked at was the cross product, and I don't think I'm quite finished with that, so I will just wrap it up with that cross product. And then we'll look at something called determinants, which is related to the cross product. There is this rule of thumb you can use to calculate the cross product, where you use determinants. It's very handy to know generally. And then we need to get started on the new topic, which is linear algebra. And to get started with that, we should understand the straight line in the traditional form, y equals x plus b, in a form involving a normal vector to a known point. And in a form that involves a normal vector without a known point, although you can easily find one. And really the most important form is the parameterization of a straight line, where you use a direction vector and a point. And finally, we'll take a look at the plane equation before we dive into what is actually the topic, which is systems of equations. So all that over there, that's something you've had before. So I'm going to go through it pretty quickly, and we won't stop and do exercises on it. It's just to remind you what the concepts mean, and then I might just do a couple of examples. So let's dive into it. The cross product, what was it again? Let's go through it. Quick walkthrough. Course product. Last time we saw that vectors cannot be multiplied, but they can be dotted and crossed, but there is no such thing as multiplying vectors. However, there is something called a vector product, which is the same as a cross product, and it is written as vector A crossed with vector B, and out comes a new vector. So when you cross two vectors, you don't get a number. Like when you dot two vectors, you get a new vector. You can only cross vectors if they are three-dimensional, so you cannot cross two-dimensional vectors. So it all takes place in the space here, and you need to imagine that the two vectors you're crossing lie in a mathematical plane. So if this is one vector, and if this is the other vector, then it is a three-dimensional vector. And if it's a two-dimensional vector, then it's a two-dimensional vector. So if this vector is called vector A, and this one is called vector B, when I cross A with B, I get a new vector, perpendicular to both, pointing up like this. You determine the direction it should point by using the right hand. You take the four fingers that aren't your thumbs, and let them rotate from the first vector in the cross product to the second one, like this. So you need to imagine the four fingers rotating in that direction in 3D, and now your thumbs will point in the direction of the cross product. So this here is the commutative law of multiplication. Application does not apply to cross product.
What does it mean? The order is not irrelevant. If I could.
Crossing A with B does not give me the same result as crossing B with A. Instead, I get almost the same vector. I get one that lies on the same line, has the same length, but points in the diametrically opposite direction. Like the vector pointing down here, which has the same length as that one, but just points in the opposite direction.
That is why I say tick B.
So if I switch the order of operations, I end up with it instead of that. And you can also see this with the right hand rule, because now I need to start with B and rotate over to A with the four fingers of the right hand. And now Thomas will start to slow down. And this vector is the same as the one I would have gotten if I had calculated that one and changed the sign. So it is the same as minus A at B.
So how long is this cross product vector?
Yes, it has been defined. So here comes a definition. Words and definitions in mathematics here are not meant to be understood. Just accept it. Someone decided how long it should be, and we will just accept it and say, okay, that's how long it is. Later, we'll find out why it was a good idea to define it that way. And the length of the cross product vector has been defined as the length of one vector. Multiplying the length of the other vector, multiplied by the sine of the angles in between. And I can't make that swing, you know? And the angle phi is right up here. It's the angle between vector A and vector B. So last time we saw that the length of the cross product vector precisely corresponds to the area of the parallelogram spanned by the two vectors. So if we look directly down onto the plane,
If this is weight B and if this is weight A,
then A and B will form a parallelogram unless they are parallel. And if they are parallel,
they're on the same
line.
one, and then it does not span a parallelogram.
But what if those two are
Four
not
is not the
parallel?
parallelism expounder. It's a parallelogram.
It looks something like this if the areas now straddle. And that area is exactly the length of one times the length of the other times the sine of the angle between them. And that area we called AP last time. And that is the length of vector A times the length of vector B.
And multiplied by the sine of the angle between them.
So the length of the cross product vector is defined in such a clever way that its length exactly corresponds to the area. So if this vector here is 7 in length, then the area is 7 square meters if you're measuring in meters. If you're measuring in inches, then it's 7 square inches.
And if you're an astronomer, that's 7 square light years.
Or 7 squares astronomical unit. An astronomical unit distance from here to the sun, 150 million kilometers.
So we have defined how to cross the 3 basic unit vectors I and k with each other. We'll go over it briefly again. If we have a coordinate system here, where this is the z-axis, and this is the x-axis, and this is the y-axis, so there is a unit vector in each of the 3 coordinate directions, and if we start them at the origin, the 3 unit vectors look like this. They are all unit length, so there's one going from there to there, another from there to there, and one more from there to there, and they are called I, j, and k. So that I is the one that lies here, j is the one that lies there, and k is the one that stands here.
And then you have,
So we decided to find that across j gives k. Does that align with the other decisions? Yes, it does. Try using the right-hand rule and go from I over to j. Then the thumb points in the k direction. So that one cross that one, it gives that one.
I XJ, go call.
Det spiritual, hvis jeg kommer til fossil, er fordi
So that gives so j cross k gives
someone might think the directions match, but what about the size?
how long was it? 1. What is 1 to 1? 1. What is the angle between them? 90 degrees. And what is the sine of 90 degrees? 1. And what is 1 to 1?
Gang 1, gang 1, 1, so it fits. In cross j, it actually gives k, because the direction is determined by the right-hand rule, and the length matches our definition.
Finally, I can try to say k cross I. It gives j plus I. That gives j.
And one last thing is that if you cross a vector with itself, you get the zero vector. Is that right? Or? Oh yeah, it is, because if you cross a vector with itself, the angle between the vector and itself is 0, and the sine of 0 is 0. This means the length becomes 0, and a vector with length 0 is called the zero vector.
So I crossed at I. Is it the same as a Jew crossed with a Jew? Is it the same as k crossed with k?
And it's all equal to the zero vector. And then we saw over here that if you swap the sequence of freedom, the sign is simply changed.
You can write the 3 equations again, but remember to switch the order and keep the signs.
So I'm putting a cross in.
Giving minus code.
Oh, cool.
Good fun.
Gives minus e.
And finally,
They intersect in cabbage.
You are less fun. And it turns out that exactly what's written here is enough to find the cross product between 2 arbitrary vectors. Last time I only managed to do it with an example, now I'm doing it with symbols. So here's something clever. If I take a vector A and I want to cross it with a vector B, and I want to find the coordinates. So I just write vector A in a smart way. Because a vector A, I can just start by defining up here. If I have a vector A, and it is 3-dimensional, then it has 3 coordinates, A1, A2, A3. And similarly, if I have a B vector, which is also 3-dimensional,
It also has 3 coordinates, B1, B2, and B3.
and we have learned that only 3-dimensional vectors can actually be crossed with each other. So A has the 3 coordinates, B has the 3 coordinates. So how do I cross A and B?
yeah, I'm doing the smart thing by not writing away like this.
So I say that this vector goes this far in the x direction, this far in the y direction, and this far in the z direction. And therefore it can be written as the number of 1 times the vector I.
the number A2 gear shift j.
And the positive number A3 multiplied by vector k. This is another way to write vector A.
And they say that one has written it away as a similar linear combination of the 3 base unit vectors, I, j, and k. And this vector, I would really like to cross it with the B vector, so I'll just do that. And the B vector can similarly be written as B1I unit vector
plus B2 J unit vector plus B3K unit vector. So this is another way to write vector B.
And then it's basically just about getting started and using everything that's written above. Then you can find the cross product between any two vectors. So I say this cross that, plus this cross that, plus this cross that, plus. Then we're done. And that's what I showed you last time, just for an example, but now I'm just doing it with symbols. And let's cross that. What does it give? Well, there is I and I. So it gives the null vector. It gives a vector crossed with itself, gives a null vector. Since the angle between them is 0, and the sign of 0 is 0. So its length becomes 0. So that cross that, let's skip it. It just gives the 0 vector. Then I take this one and that one, it gives A1.
So I write A1B2 of a B2, and then it says IXJ, and IXJ gives K.
That would be cool.
And then I continue. Now I've taken this one and that one, and this one and that one, and then I take this one and that one. Then A1, B3, A1, B3. And what does it say? Cross K, and I find E. Cross K, that gives minus J. So this should be a minus. And then it should say J. So now I have this that I should not write the sign before, I'm sure.
So now I've got this and that, this and that, this and that. So I start here. A2, B1. So I just start writing A2, B1. I am waiting to write the sign because I do not know it yet. So A2, B1, and then there's J cross.
I and J prime I. We have it there. That gives minus K. Minus K.
Then I take this one and that one, and it gives me the 0 vector because it's J and J. So it was a vector crossed with itself, which gives the 0 vector. Then I take this one and that one, A2, B3. So I write A2, B3, and it was J cross K, and J cross K gave I. So now I can write a plus and then I. Then there's just the last term, that one and that one, A3, B1.
A3, B1, A3, B1. Then it says K, X, I gives J. So it was this and that. It is A3, B2, A3, B.
And then it was K cross J, and K cross J is said to give minus I. And then I'm done. Because the last one, that's KK, which becomes the 0 vector. So here is the result. It is the cross product vector. And then you look at it and think, can't you make it a bit nicer? Yes, you can. Because look, here's something with I, and here's something with I. It ends with I. And here's something with J.
And here's something with J. And here's something with K. And here's something with K.
And gather
So you can-
everything related to I. Everything related to
What does
K do? So what is it then? These are the 3 coordinate directions. So if I just write it like this, I wish I could use the next board, but I'll just have to try to continue over here. What is it that is here?
Thanks. Equal to.
So it is then,
A plus B.
I am still figuring it out.
I can write it together then.
And right here, I'll make a little more space.
Anything?
In the direction I got it here. Oh, and the J direction.
And reached.
Oh, it's getting a bit small. I hope you can read it. Let's see if I can
You
get
got it. What do I have in direction I? There I had A2, B3 minus A3, B2. Notice how beautiful the symmetry is. A2, B3 minus, and then it's just switched at the end, A3, B2. Sum A2, D3 minus A3, D2.
What I just did was factor out unit weight from those 2 terms. So now it's outside the parentheses. Then we have something with J.
And that is the environment. So here we have A3, B. And then I had minus A1, B3, minus 1. B3.
Notice here that I start with the smallest number, A2, then 3, and then 3, then 2. But right here in the middle is the opposite. you start with the first largest number, a3, b1 minus a and b3. It's a bit annoying, but you have to live with it. On the bright side, you get in a really good mood when you do the last one, because with the k, it's again a1, b2, where I start with the smallest number.
Minus a2 to d1, then a1 to d2.
Minus a2.
Do you know that?
And there you have it. That is the form of the cross product. But perhaps you noticed that everything with I must be the first coordinate. And everything related to j must be the second coordinate. And everything related to k must be the third coordinate. So here we have the first, second, and third coordinates, which means I can actually write it like this. I can rate it as a big, great vector, where the first coordinate should be here. So it is a2, b3.
I'm not even trying to write the parenthesis.
Minus a3.
b2. And I'll be at b1, 9,
A2.
a1, b3. And here it should say a1, b2, a2, b1.
Sure, we'll be gone for an hour. And then you might think, I'll never learn that by heart. But listen,
Remember
there are
to
a couple
hold.
of smart things you can look at. In the first coordinate, you need to calculate. There are no ones.
There are only 2 and 3. And then you start at the leftmost. So a2.
B3, and you take them in alphabetical order. So this is something to remember. But there is a way to remember it. This was the answer. There is a way to remember it. And that was the next point. You can actually just find it as the determinant of a 3x3 matrix. But I have not had matrix calculations yet. It's not sure that it will help you much, but I'll just tell you how the memory rules look. And once we've gone through matrix calculations, we will come back to it. So let's see if we can figure out how to make a cross product just by using what's written there.
And now I'll show you how you could have made it a bit easier than what it says there.
And that must be board 2. Here is an example. So I'm allowed to clean this offer out over here. Let's just come up with 2 vectors. So right here, I'll just invent 2 vectors as an example. Let's say we have a weight called 1 over 0 over 3, and that's my vector A.
And then I come up with another vector, vector b.
And let's say it's called 2 over 4 over minus 1. So these are just some numbers I'm making up. There's nothing special about these numbers. I'm not hiding anything. They're just 2 random 3-dimensional vectors. Or maybe there was a single hidden thought. I've tried to make sure they're not similarly dependent.
What does that mean?
If they were linearly dependent, it meant that one vector could be produced using the other by multiplying the other with a constant. So they are linearly dependent. For example, if I now multiply that number by 2, I get 2. Multiply it by 2, I get 0. Multiply it by 2, I get 6. So if I had chosen 2, 0, 6 over here, then this one over here would have been linearly dependent on that one, and they would have been parallel. And then I would have gotten a 0 vector when I cross them. For the 2 parallel vectors cross with each other, you get a 0 vector. So I just made sure to give something that was not a 0 vector, because that would have been too easy and boring.
So if I need to cross them, it goes like this. What is 1 is 1.
It's A2, A3, B1, B2, B3. So we can follow it broadly through this formulation.
So it's the cross product between the 2 vectors.
first coordinate. And then we need to remember to look over there. There are no ones because we're in the first coordinate, starting with the smallest. So it's A2, B3, A3, B2, A2, B3, which means 0, minus 1.
And then I was supposed to write a 9 and stand over there.
And
It
there
must not
will
be anyone,
a
so it is
plate
minus.
from 3B2.
So subtract that from that.
Then it's minus 3.
Garnefika.
Do you agree? And in a moment, we can figure out what that gives us. Then we'll move on to the next line. There are no 2s. Instead, I need to start with a 3. So A3, B1. So A3, B1 is 3 times 2.
Minus, and then I say A1.
B3, then once minus 1.
And the last one says A1, B2, so I have to say it, multiply it. That's 1 times 4, minus A2, which luckily is 0.
And then multiply by B1, which is 2. And then we can figure it out.
That gives 0, that gives minus 12. And here it gives 6, and here it gives plus 1, and 6 plus 1 is 7.
And down here it gives 4, and this gives 0, so it just gives 4.
So if I have calculated correctly, that should be the cross product vector. And then someone might just be wondering, what am I supposed to use that vector for? One thing that's true about this vector, if you've calculated it correctly, is that it stands perpendicular to that one, and it also stands perpendicular to that one. And we saw last time that if two vectors are perpendicular to each other, then their scalar product should be 0.
Let's give it a try. Let's see what A crossed with B is.
There's just one weight here. What do you get if you poke it with A?
We hope it gives a sense that the rain has been put on hold.
So I say that times that, plus that times that, plus that. So
times
that time, so it's here, minus 12 plus 0 plus 12, and minus 12 plus 12, that's 0.
Minus 12 plus 12.
It's 0, but then we know that it is
Across B, better.
perpendicular to A vector.
Then we can do the same, where we try to take this cross product and dot it with that one.
So we take A times B.
And dot it with B. And we hope to get 0, because if not, we have miscalculated.
Suddenly I say that time it's minus 24. Plus times them, it is 28. And that time it is minus 4.
And minus 24 minus 4, that's minus 28, plus 28, that's 0.
So money counts.
A at B
Stands perpendicular as well.
is also angled on B.
Take care. What else can we use it for? Oh yeah, we can take away the length of this one. What do we get then? Then we get how big it is, yes. These two vectors span in the form of a parallelogram. Just think about how brilliant that is. Here you have two vectors pointing in a strange direction in space, and they span a parallelogram that is tilted in a completely strange direction.
Strange, which vibe in the room and which vibe in the final and stuff like that.
Then we can also find the area of the triangle they span. You just have to take half of it, right? So imagine these two vectors positioned in some strange way in space here and form a parallelogram. We can find this area here. We can also find the area of the triangle here in space, so it lies completely skewed in space. It's still not on a plane, of course, just like all triangles.
At least in some narrow stone room that curves.
You can also find the area of the triangle. You just need to remember to divide by 2. So let's try to find the area of this parallelogram here.
AP, we're toppling A.
That's vector B, and it might not actually look like this. I just drew it to help you imagine it.
I just need to find the length of that vector.
So I need to find the length of the cross product vector.
And there we learned last time that the length of a relay is 10. Square root, yes.
The sum of squares of the coordinates. And squared plus and squared plus and squared.
It is minus 12 squared.
Plus 7
squared plus 4 squared.
And then I'll start calculating it. So can't we 144 and 7 is part of 49. Remove the 16.
What does this make? It's just under 200. She's 7, so she's 193.
Do you know what goes in there? I'll just try to check it again. Do you know what's in it? I'll just try to figure it out once more.
It says 65 and 65 to 09.
Good to do what needs to be done. You can just do 209th. That's Marty the Magician's favorite result. He doesn't even bother to calculate it as a decimal.
It is just the area of that parallelogram.
And if I wanted the area of the triangle, I would just say half afterwards. Simply divide by 2. And that means with the cross product, you can find the area of a triangle if you know which 3 points in space describe the triangle.
Because if you have the 3 points in space, then you just form a vector from one
From that point to this point. If you take the cross product of the 2 vectors and find its magnitude, you have the area of the parallelogram, and then you divide by 2, and you have the area of the triangle. And it's really clever that you can do that, but you can also use it to calculate moments in mechanics with Leonard, or you can use it to find the force on an electric charge that is moving in a magnetic field if you need to deal with electromagnetism one day. And there are other things. So that was the cross product, and I promised to show a mnemonic here that allows you to calculate this cross product even faster than what I did here. So I'll just do that over here. Let's just say it's still board 2. So if I am going to cross A with B,
You can do this trick here. It's called forming a trick.
We cannot pull a trick. And what is it? Well, it's just
a rectangular grid with 3 rows and 3 columns. Yes,
There
3
is
rows and
nothing.
3
It's
columns.
dangerous enough, maybe.
It looks like this.
I, J, and K. You just start by writing that. So here
The
in the
first
world
row,
of bugs,
The first vector,
It's called 103.
102.
And then in the next row, you write 241.
2, 4 minus 1.
Now comes the move. You start by placing your hand over this column here. And then you say this times this minus this times this. That times that is 0. And that times that is 12. And I was supposed to say that times that minus that times that. So it gives minus 12. Can you see it?
so this gives minus 12 in the I direction. Yeah.
Because it was this pillar I was leaning against.
And isn't it also true that I got a negative 12 as the first coordinate point? So I'll do it.
Then you cover the next column with your hand, and you say, this times this minus this times there.
And remember to change the sign at the end.
And that times that it's 1 minus that times that it's 6. And then 1, 6, it's 7. Then change the sign, it's 7. And finally, you hold your hand, or actually your arm, over this column and say, this times this minus this times this gives 4 and 0. So it is 4, which is plus 4k. And there you have 1, it is the cross product. And it is the same one that is here. Because minus 12 in the I direction plus 7 in the J direction plus 4 in the K direction, that's the vector that has a first coordinate of minus 12, a second coordinate of 7, and a third coordinate of 4. So again, you hold here and say this times that minus this times that. Then you held here and said this times that minus this times that. And remember to switch the sign. You only need to switch the sign in the middle. And at the end,
Back then, this
And
video.
it turns out that's exactly how you calculate what's called the determinant of a 3x3 matrix, which we'll get to soon enough.
so actually you can find
the
the cross.
product. Each own determinant is a
It's actually called the pseudo-determinant of a 3x3 matrix, where the top row consists of the 3 basic unit vectors I, J, and K. And the next 2 rows are the 2 vectors you want to cross.
So that was the cross product. And maybe I should write a quick little problem on the board for you. And then I'll pause while you try to solve it, just so I can see if it makes sense. Can I wipe the board? Is that okay, son? Here's a little task for mental calculation. Okay, well, so we are given two vectors, vector A, 5, 3, minus 1, and move
1, 2, minus 3.
and here come the questions. See you later. A cross B. Stir small b. It is clean. Times b. Where have I ended up? And question C. Determine the area of the triangle formed by vector RB. Who is the area of the triangle spanned by vector A and B? Sophie, if you want to pause the camera while we work it out.
Okay, let's take the task on the board.
In the question, we just had to find the cross product between A and B. The cross product between vectors A and B, we use the memory rule there. We write I, J, H. We take the basic unit vector, then we write the first vector as the first row and the second vector as the second row. So 5, 3, minus 1. 5, 3, minus 1, and 1, 2, minus 3, 1, 2, minus 3. Then we just use the mnemonic rules. We go here. That times that, minus that times that. That's minus 9, minus minus 2.
It must be negative 9 plus 2. That's negative 7. So the first coordinate becomes minus 7. I'll pause here. That time that.
It's negative 15 minus negative 1. It is minus 14. Change the sign. It is 14. Because in the middle, you have to remember to change the sign.
So here I have it. This times this minus. This times this. That's 10 minus 3. That's 7.
So that was the answer to the question. And if you prefer to write it like that, you can also write it as minus 7 times the unit vector I.
Plus 14 times vector j.
And plus 7 times unit vector k.
It's the same vector. So there was question 2. What does the dot product between AB and A calculate?
Then the stock product should be between A cross B.
So there is one weight.
I will cover that with A.
Well, how do we do it then? Right, we said this is indeed the cross product vector. Minus 7, 14, 7. And I need to dot it with vector A, which is 5, 3, minus 1, 5, 3, minus 1. And then you have to remember how to do a dot product, which you do by saying this times this, plus this times this, plus this times this. So first coordinate times first coordinate, and so on down there. So what does that give? Minus 35.
And so here it is plus.
So where to before?
Plus 42.
And then it gives negative 7. But minus 35 minus 7 is minus 42. Plus 42 is 0. And of course, it's not too surprising, because if it hadn't been 0, we would have calculated it incorrectly. Because we know that this vector should be perpendicular to both vector A and vector B. And then there's the last question. If the area of the triangle that AB spans, well, we know that the area of the triangle, if we call it 80 for the area of the triangle, it's half the area of the corresponding parallelogram they span. And therefore, it must be half the length of the cross product vector.
So I just really need to find the length of this weight for that.
And then I need to do half. So that's half times the square root of 7 squared plus 14 squared plus 7 squared. I don't need to say minus 7 squared because it's the same as 7 squared does. So it's just 49.
Plus, and that's squared, 196.
And then plus 49 again. 49 plus 49 is almost 100, just shy by 2. So that's 98 plus that 294. So it's
The cloakroom number is 294.
half.
And then we're done. That was Jaeger and Tricond.
So vector calculus is an insanely powerful tool. It can be used as a shortcut to calculate all sorts of things that would otherwise be quite complicated. For example, the area of triangles in space, which are tilted in some strange way, where you cannot immediately imagine how else you could find the area. Say, shall we start with the concept of determinants? I'll tell you a bit about it, but maybe we should take a break first. Let's say we'll have a break until it's 2 minutes past the half hour.
Otherwise, shall we say 33 minutes past? No, 10 minutes. 33 minutes past.
Okay, let's continue. And the recording has started.
So let's take a quick look at the concept.
That's the concept of determinant at the level you've heard it before, just to remind you of what you've once heard. And then we go deeper into the concept of determinants later, where it is not only the determinant for 2-dimensional vectors, but also for 3-dimensional vectors and n-dimensional vectors.
So let's take a look at the concept of determinants. So the headline is now determinant.
Determinant is something we've introduced to determine whether vectors are independent or dependent on each other. And what do we mean by that? Well, if I have a vector that looks like this,
It definitely cannot come off. And then I have another scale, which looks like this.
I call that vector B. Then you say that the two vectors are linearly dependent, as I've drawn them there, because you can create vector B just by taking vector A and multiplying it by a constant.
Because vector B points in the same direction as vector A.
And this means there's only a scaling constant difference between them. So vector B can be expressed as some number k times vector A, because vector A just needs to be stretched a bit and it slowly becomes B.
And that's what you call linearly dependent.
That's fine.
And A is just as closely dependent.
So if two vectors are linearly dependent, there exists a constant you can multiply one vector by to produce the other vector in that way.
But there are also vectors that are similar to independent ones.
I think of it as completely independent ingredients. So for example, if you're making pancakes, you need a bunch of independent ingredients. You need flour, salt, vanilla sugar, eggs, and milk, and maybe a little bit of lemon and some beer if you want to make really good pancakes. And all those ingredients are just about independent of each other in the sense that you cannot get eggs by constantly multiplying flour and water. If you use more flour, you will not get eggs. In the same way, these two Victoria drawings here live their own lives. So one can correspond to flour and the other to eggs. And you can never create one from the other by scaling constantly. So if you have two Victoria illustrators living their own lives, just like those two do, they are not parallel. And now we call them linearly independent.
So here are vector B and A.
right nearby. Independently,
And I want to say
up
thanks for
here
that.
are the parallels. And down here, it's so lovely. Anti-parallel. I never fully keep track of how many others are supposed to be on accounts concurrently, but if any of you think there are too many, you should remove one. And then they introduced a tool called the determinant. It comes from the English word to determine, which you can use to decide, to establish if two vectors are parallel. And we can give a quick example to show how it was invented. Let's take a vector of 1 over 2. So it's
nice.
a two-dimensional vector, since it only has two components.
Because it only has two coordinates. And let's take another vector B, called 3 over 6.
So it's also a two-dimensional vector. And now I want to determine if the two vectors are linearly dependent or independent. To do this, we use a clever trick by calculating what is called the determinant of the vector pair A and B. And we write it like this. You write det, which is a short form for determinant, and then you write the two vectors you want to find the determinant of, separated by a comma. And what you do is simply say this times that minus that times this. So 1 times 6 minus 2 times 3. 1 times 6 is 6, and 2 times 3 is also 6. So 6 minus 6 gives exactly 0. And then your brain might just think, oh, it gives 0. So what? Well, you can probably imagine that if that vector came about by multiplying that one by a constant. So it would give 0 if that's the case. Because when I say this times this minus this times this, it will result in 0 if this is a vector that emerged by multiplying that vector by a constant. And I ensured that here, when I came up with the exercise, because 1x3 gives 3 and 2x3 gives 6. So this over here is a scaled version of that vector. Therefore, they are parallel. And it is determined when you calculate the determinant, it determines it for you. Since the determinant is 0, I can conclude that vector A and B are 0. They are parallel.
And that is the same as saying that they are linearly dependent.
This is the same as saying that they are linearly dependent. So one can be produced from the other by multiplying with a number, you could say. Let's take an example where they are similar to independent. Example 2, I can reuse that vector, for example. So let's say I reuse vector A, but I invent a new vector B, which is called 1 over 2. And now I just need to make sure that vector B cannot be written as a constant multiple of vector A. So I can easily do that by reusing the number 1 and then writing a new number here, a new number like 2, for example, negative 2. Now it is impossible to take this vector and multiply it by a constant to get that one over there, because you have to multiply both coordinates by that constant. And what should I multiply 1 by to get 1? 1. But if I multiply 1 by 2, I won't get minus 2. So they are definitely linearly independent, and that's revealed if you calculate the determinant for the vector pair.
So what does the determinant become then?
It is that times that minus that times that. So that times that is minus 2. Minus that times that, meaning minus 2 times 1, and I can figure out what that equals.
Minus 2, that is minus 4.
Now I have minus 4, which is not 0. And since it is not 0, it is directly dependent.
So far, so good. But here it means that it's the number negative 4. Besides not being 0, does it mean something more? Yes, it does.
The downside matters.
Which is interesting. It actually means that the space, we transform it, and it gets flipped upside down when we get to something more like algebra. And the fact that it gives a 4 means that the two vectors span a parallelogram with an area of 4. It also means that the entire universe is scaled by a factor of 4, when you do linear transformations with a determinant that gives -4. But we'll get more into all that later. What you learned in high school was just that if this results in -4, you just need to take the numerical value to get the area of the parallelogram. And the new thing you have learned now is that it can be used to determine if two vectors are independent of each other, whether they are two independent ingredients for the pancake batter.
Or that one child should be the addition of the other.
And this is important because we need to look at what it takes to span a space. What kind of spaces? For example, the space we are in, which is three-dimensional. It takes precisely 3 linearly independent vectors to span this three-dimensional space. No more, no less.
There were exactly 2 nearly independent ways
To span the two-dimensional space. Nothing more, nothing less.
and that requires
Exactly, and linearly independent vectors and spanning n-dimensional spaces. And closer decisions on the importance,
Force is never near
independent
a
or not, you can use the determinant for that. It can determine it.
Go ahead.
And soon we'll see that it can also be used to analyze something geometric, because the next thing we'll do is quickly review the straight line and share something slightly new about the straight line. It might be new, or maybe you've seen it before, but we need to know it anyway.
Let's dive in and repeat
the right line before we get started with what it really
Of
is.
our curriculum, which consists solely of equations.
I just want to make sure you remember that. The most important thing is to have a straight line. Can I erase this board?
The board is done.
So our extra tax is now the straight line.
So if I now have a point on the board and ask myself, how many straight lines go through that point? The answer is infinitely many, namely all the infinitely many straight lines that can lie and rotate around that point. But if I ask how many straight lines go through 2 points, it is clear that there is one and only one. So a straight line is uniquely defined if you ask if you have 2 points. So wherever you encounter data, if you only have one data point, you can say absolutely nothing about the trend of that data, nothing. But as soon as you have 2, you can at least say whether something is increasing, decreasing, or stable. And that is why the straight line is very important to understand. It is because all growth, no matter how complicated it is, can be approximated with a straight line, as long as you do not move too far away from the point you are interested in. For if I have a sphere that looks like this, and I am interested in reality right here, but then I just zoom in there,
because that's where I'm interested. And what the reality looks like there is a day.
that is what we can let you acknowledge. So the straight line is the foundation for understanding all advanced mathematics, because all the complicated math we approximate with straight lines, if we can get away with it. And it's called a first order linear approximation to reality. Is the Earth flat? Yes. As a first order linear approximation to reality, it is flat. If you want to understand the Earth a bit more, it's round, but it's almost perfectly spherical. As far as we know,
And we even looked at it from the outside.
Then you are quite sure it is nearly spherical. And how spherical
it was actually
that close? Yeah, it's
It's
weird.
difficult.
Made a sphere in the lab that's as round as the Earth.
But they've made some that are better. They've made one, I believe that's 3 inches in diameter for the gravity probe B satellite. That sphere they made is so round that if you blew it up to the size of the Earth, the difference between the highest peak and the lowest point would be 15 centimeters. That's how round it is. And it's grown. It's grown from quartz crystals, and it's grown so precisely that all the quartz crystals are identical except for 1 in 10 million. So it's completely uniform, a wonderful material that the sphere is made of. And you can use it to measure, and Einstein is right, that space curves near large mass objects.
With a brush, a straight line.
There is one and only one straight line that passes through those 2 points. And we have learned that the equation of a straight line looks like raised y, meaning with a times x plus b.
That means if we draw it on a graph, where this is the y-axis and this is the x-axis. So a guideline could look like that.
for example. And it is characterized by where it intersects the y-axis. That's the number b that is there. And then it's characterized by its slope. And that means if you place yourself at a random point on a straight line and move 1 unit in the positive direction of the x-axis, how much do you need to move to hit the line again? The distance you need to move is the slope. So if the slope is positive, you move up to hit the line again. If the line has a negative slope, you move down to hit the line again after taking a step to the right. And if you're still on the line after taking a step to the right, the slope is 0. Once upon a time, you learned that if you know 2 points and we are on a straight line, when you call them P1 and P2,
Good to hear from you.
then you can find the equation for that line. So let's say that point P1 has coordinates x1, y1, and point P2 has coordinates x2, y2.
So we take a drawing. I'm describing something that looks roughly like this.
Here is a point P and
G1 with x coordinate x1 and y coordinate y1.
And here's the second point, P2.
With corresponding 2 coordinates x2 and y2.
Kim!
And just like before, we can conclude that there exists one and only one straight line that goes through those 2 points. And I am trying to draw it now. And now you can look at 2 similar triangles here, because the slope means that if I take a step 1 to the right, how far is it here? Who is in it? But now I'm not taking a step at the same height. I'm taking the step all the way out there. And then I look at this triangle compared to the small triangle. And I conclude they're similar because they share this angle here. And they're 90 degrees in the corner. Therefore, the last angle up here must also be the same. So they have the same angles. And when you have 2 similar triangles, it applies that one is a scaled up version of the other. So if I stick a compressor hose in there and inflate, it becomes the larger triangle. And that means the whole triangle is scaled up by the same scaling factor. This means that the ratio between this side and that side is identical to the ratio between this side and that side. And if you write it down, it says A over 1. It was that side divided by that side, not the same fraction as there over that. But how long is that out here?
Yes, it's y2 minus y1.
And how long was this side? It was times 2.
Minus exits.
And here I have the formula to find the slope of a straight line. When you have found the slope of a straight line, you can just insert either the coordinates of P1 or the coordinates of P2 here, and then find B. For example, if I enter the coordinates of P1, it says that y1 equals a times the x.
That was exciting.
And there I can isolate B. So if you want to know B, it's just to say that B, oh, it shouldn't say B, it should just say B. There's only one B. It should just be B and A, but exit and y1, because it belongs to point P1. So now I can find B as y1 minus a exit. And that was one way to find B.
And I have used it to do that.
But I could also use P2 to do it, because I know it's not
If
that
I
hard.
input x2
In place of x, go to coordinate y2.
So I also know that y2 aligned with x2 plus b. So b can also be found by saying y2 minus ax2. And in that way, if you have 2 points, you can uniquely define and find a and b. And then you have the equation of a straight line. And that was all stuff you had. So it went pretty fast, right?
This shows that you can also write a straight line in this form.
And that just requires an explanation.
So now we'll add a subheading to the straight line called
Fart line.
using VHA by using standard weights and a known point. For right angle, we help the normal vector and the known point. Okay. Imagine now that you have a known point here. And because it is known, it is called P0. And this arrow indicates that it is a known fixed point. It does not move. It is welded in place there. And point P0 has two coordinates,
X0 and Y0.
and as you will see in a moment, X0 and Y0 correspond here in my line.
What was it you noted down?
And now you might ask yourself, how many straight lines can be found at
If
point
it goes
P0?
through.
And the answer is, as usual, infinitely many.
But what you do now is say, okay, if I then
So
compare,
you have a vector originating from PCO, because I choose to let it start from PCO for a vector.
the starting bounds should fix it.
So I choose to start, and I name that vector n.
As an abbreviation for normal. It now
So
turns
what
out
I
that
want to say to you is the vector is perpendicular to the line that needs to go home.
So it's the normal vector.
And now one might ask the question, how many straight lines are there that, besides passing through P0, also need to be perpendicular? And then there was only one. Just like you can uniquely define a straight line using 2 points, you can also uniquely define a straight line using 1 point and a known normal vector.
So now I'm drawing, at least I'm trying.
And draw the only line that exists, which passes through PEO.
And which at the same time is perpendicular to in.
And I call that line alone. So here is alone. And here is 90 degrees. So the line is perpendicular to N. And there is only one version of the line that both goes through P0 and is perpendicular to N simultaneously. So what I could do now is say, okay, if I then choose a point blindly, like this, so there are two possibilities. Either I hit the line or I do not, because the line is here. So a blind point can either be on the line or next to it. And now I can ask myself this question. What is the condition for the point I chose to actually be on the line? I can come up with a clever condition. Yes, I can, because if I choose a point blindly, when it becomes that, I can form a vector from PS down to it. And this is a random point, so I'll call it P. And because it is completely random, it has two random coordinates, X and Y. And now I could just ask myself, the vector that starts at PO and ends at P here, is it perpendicular to it? If it does, then P is on the line. If it doesn't, then P is not on the line. Can you see that? Because if I landed on the line when I chose my point at random, then a vector from PO to P would precisely be perpendicular to N, because the line is perpendicular to N. And we know that the dot product of two vectors is 0 if and only if they are perpendicular to each other. So I can establish a condition for a point to lie on the line, and the condition looks like this.
if and only if P is on loan.
This means that a vector from P not to P is perpendicular to M. That's the condition. The answer, a randomly chosen point, lies on the plane. But we know this means that the vector from P0 to P multiplied by the normal vector for the plane must equal 0. Because we know that two vectors are only perpendicular if their dot product is 0, and the dot product is 0 only if the two vectors in question are perpendicular to each other. Therefore, the arrow applies in both directions. And that's what we learned
And
together.
only if Premio-Skiller is shown.
So is er.
And this here, this is called for the same reason.
The equation for a straight line.
The line is from a straight line.
And which straight line does this equation represent?
We can read it aloud on this. This is the equation for the straight line that goes to PCO and stands perpendicular at the end. And there's only one. See, we have uniquely defined one for the line.
Straight line.
Help us if you try
see.
to write down the dot product, it actually shows that it gives exactly what is written here. So I'll just come up with some coordinates for that normal vector. Let's say the coordinates are alpha over beta. They are just two numbers, two coordinates. Let's try to find the vector from PCO to P and write down the coordinates for it. Now let's see if we can remember back to our high school math. How do you find a vector from one point to another point? Oh yes, you take the coordinates of the endpoints and then subtract the coordinates of the starting points. So if I need to find a vector that starts at P0 and ends at P1.
Look here, this was a lucky P. It was on the line. This was an unlucky P that wasn't on the line.
But in both situations, I can find the vector from P0 to P by taking P's coordinates and subtracting P0's coordinates. And P's coordinates were x, y. And from there, I need to subtract P0's coordinates, which were x0, y0. So now that I have the coordinates for both the vector from P0 to P and the normal vector, I can calculate the dot product and see what it gives. So what does it give? Yeah, it's the first coordinate times the first coordinate plus the second coordinate times the second coordinate, because that's how you multiply two vectors that are two-dimensional. So it's alpha times x minus x0 plus beta times I minus I0 equals 0. Here it is. It is the equation for a straight line. And which lane is this the lane for? This is the lane for the straight line that is perpendicular to the vector with coordinates alpha over beta. And it definitely passes through the point with coordinates x0 and y0. Well, now questions. By the way, you can also use that mindset to find the equation for a plane when we get down here. So let me just show you an example of that type of straight line where I point over here to the left.
There were no objections.
We just call it 375. That's what it is now. So here comes an example. You might ask your neighbor, dear neighbor, what is this? And if your neighbor is a mathematician, they would immediately say that it's just the equation for a straight line. And then I would ask him, which straight line? If he's a mathematician, then hopefully he'll answer the straight line that has a normal vector with coordinates 2 over 3. And he can read them directly when the normal vector has the coordinates 2 over 3. And which passes through a known point. What known point? Well, x0 should be 1, y0 should be 5. So the known point P0 is called 1.5. Note that the negatives were included in the standard form.
So you need to look for minus to find x0 and look for minus to find y0.
And now I could ask him, dear neighbor, how many straight lines exist that pass through the point 1,5 while standing perpendicular to the vector with coordinates 2 over 3? 1. There is only one, and therefore I can draw it. So it's pretty easy. Instead of slope and intercept with the y-axis, I can draw that straight line just by starting to plot the point called 1,5. 1,5. We assume it is right there. So this is point P0. Now I will draw a vector that goes 2 across and 3 up. Let's just start here. 1, 2, 1, 2, 3. It looks approximately like this. So that's N. This is point PO. And now I just need to draw the only straight line I can, which passes through that point and is perpendicular to the vector. And it looks roughly like this. Something like this. So that is it. That is lane L. So I can see that it's another way to think about how to draw a straight line. Now you just have a known point and a known normal vector. Any questions? Is that clear? Okay. So we come to this point here. What is this now? X plus B plus C equals 0. That's also a direction. And we need to see why that is. That's right. Because if I look at what's written down here, which was a straight line, I can just multiply out the parenthesis. We multiply out in that parenthesis and continue the story here. Then it will say alpha times x plus beta gang u. Now I've taken that times that, and I've taken that times that, but I must also say that this times that is minus alpha x0. I'm taking that now. Minus alpha x0, and then minus beta y0. Minus beta is 0, and of course all of that still has to be equal to something, just like it was before. But now you can see that these are Luther constants. Because x0 is a constant, it was precisely that point fixed at the welding point, and y0 is a constant, and alpha and beta are the two constants that describe the first and second coordinates of the normal vector, so they are also constants. So I could basically just note all of this. And if I just want to separate this form from the one down there, I can certainly do
I
that.
can go ahead and rename this to an A and that to a B.
So now you can see it actually just says ax plus by.
You look right at 0.
This is also a straight line. It is the same straight line as before. That one is the same straight line as this one down here.
But just notice one thing. That's not the attitude.
That's not the good old AF that describes the slope for a proper level.
And that is not the good old B, which describes where it intersects the y-axis. So what are A and B then? Well, it was just a renaming of the two. So it was the first and second coordinate to the normal vector. And notice another thing. If a line is in this form, what do you get? A fixed point. You know that this line goes through the x0, y0 point. But up here, that information is gone. Where did it go? Into C. It has just been restructured into one number. You cannot directly read a point anymore. Does that mean that if I have a line in this form, I cannot find a point that the line goes through? No. Of course it does not mean that. It is just a bit harder. It is no longer obvious to me. So let's take an example where you can see what I mean.
Let's try to write something like this. 2x plus 3y plus 4 equals 0. What is it? A straight line.
So if I ask my neighbor what it is, he'll say, if he's a mathematician, it's a straight line. And then I ask him which straight line, and he says, it's the straight line that has the normal flipped with the coordinates 2/3.
So he can read it right away. He can tell me right away that it is at the right
On
angle.
this vector.
That straight line. And then I say, can you name a point, you know, that line goes through? And then he might
Yes,
say,
I certainly can. Just set y.
Congratulations. And then that gives 0. So find an x.
so he just picks one and figures out the other. He can also choose x and work out y. But what if I choose y to be 0? So let it be 0. What does that leave? 2x plus 4 has to be 0. So x has to be minus 2. We can see that we have just solved that simple line. We subtract 4 from both sides, then divide by 2. And that means this point here, called P,
Needle. Minus 2.0.
it lays on the line. So with the normal vector and that point, I can draw a line.
But you have to calculate a point yourself.
So what have we learned? A straight line can be written in the form x plus b, which we know all the way back from elementary school. It is the slope coefficient times the y-axis. But we can also write it in that form where you have a known normal vector with coordinates alpha and beta, which passes through a known point with coordinates x0,
I0.
and
And
that's
a straight
also
line.
a form.
Just written in a different way.
And that's also a straight line. With a known normal vector, a over b, where this a and b are not the same as that a and b, you need to be careful about that. But where you need to find a known point yourself, if you want to plot it. This up here is called a straight line written in explicit form, where you can see that y is a function of x, and the formula is explicitly given. Here, f is explicitly given as a function of x. Down here, it's called a straight line in implicit form. Because here x and y are intertwined, you see? This means you have to work hard to isolate y. And you do that before you can explain how the function rule looks. Are you ready? So far, so good. Now let's see what this is below. It's also a straight line.
So there are many different ways to describe a straight line in 2D.
And it turns out that this one, in this course, is the most important. The one coming up now. I'm picking up the pace a bit, just in case you do not remember seeing it before. So board 6.
Him. How quiet is it?
Here I have a point.
That does not move, and I call it P0. It's Swiss fast. And P0 has coordinates X0 and Y0. And then I could obviously ask that question, which I don't feel like doing. How many straight lines are there that go through P0? And the answer is infinitely many. But then I could ask, how many straight lines are there that, in addition to passing through P0, also need to have the same direction as this vector? That is, be parallel to that vector. Now we can see that there is only one line that goes through P0, which is also parallel to that vector. And the line looks roughly like this. So it is easy. And this vector here, which has the same direction as the loan, is called a direction vector for the line. And let's say that the direction vector has some coordinates, which I call R1 over R2. And now I'll just draw the whole story inside a coordinate system. So here's my y-axis. And here is my spare axis. And then I look at my drawing here and say, how can I do that?
Can I describe a random point located on the mortgage?
Yeah, just got it. I call that P. It's a variable point. It can be anywhere, but it has to be on loan. It must be on loan. So P is a point on the line loan, and it has coordinates in X, Y. And how can I now describe that point? Well, I might start by making a new drawing, because I can see that my current drawing isn't great for what I want to show. So I think I'll just try to draw it again below, because it's getting a bit messy. So to make sure you understand what I'm doing, I'll just draw this diagram again, but in a slightly new spot. So everything I'm about to do makes sense to draw. So here's loan. I'm a bit stuck up here. And here was a point, which we know lies on the line. I call it P0. It corresponds to that point right there. And here's the variable point on the line, P.
A directional vector. Are there any crayons here? No, there aren't.
So there are no teaching points today.
So here it is.
Next step, Tom, yes. What can I do now? Well, I can create a vector from the origin, which is here, the starting point of the coordinate system, up to P0. Boom. That vector starts at the origin and ends at P0. So it's called the OP0 vector.
So this is OP0 vector.
I can also create a vector that starts at P0 and ends at P. It is right here. And since it starts at P0 and ends at P, I call it the POP vector. So that is the vector from here to there. And finally, I could form a vector that starts at the origin and ends directly at point P. Therefore, this vector starts at the origin and ends at point P, which I call the OP vector. And now you can see in my drawing that if I use vector addition, this vector plus this vector gives that vector. Because if I first go from here to there, and later go from here to there, where have I effectively gone from and to? Here to there. And since vector addition was introduced to describe movements, so it must be such that this vector plus that vector equals that vector. And I can write this as vector O, P, 0. Add it to the POP vector. There must be the vector OP. So I can write that down. And at the same time, I can say something else. The vector from P0 to P and the R vector, they seem dependent because they are parallel. And what did it mean again that they were similar and dependent? Well, one can be derived from the other through multiplication by a scalar. So that means if I take the R vector multiplied by some suitable number, can be stretched to what it is supposed to be. This means that the vector from P0 to P1 is the same, can be written as some appropriate number t multiplied by the direction vector, and they are parallel. Therefore, it is possible. They are equally dependent. So I can plug that right in there. So let me now write out what the OP vector is equal to. The OP vector here is equal to this plus that. That means OP0.
Plus P0P. But P0P
the same
is
as the scalar t times r, where r was the direction vector. And here I have now described what? All vectors that start at the origin and end at a point on the line. Therefore, I have essentially described the line.
Origin.
Yes, thank you for letting me.
It is mine alone.
The vector that's here, what is it?
Scale yourself up on OP0 plus this direction vector. Stretch it each time with some number. Let's see what I write here. So here, I have described a straight line. I can just let t go through all real numbers, and I will get all the points on the line described.
Seriously, if t actually runs
In terms
through
of
your
numbers,
positive
I get all
real,
the points.
it's right here.
Sorry, from here in that way out. That means t is positive. And if t is a negative number, and I multiply r by a negative number, then it flips. So I describe all the points that are down here. So here's a description of all the points that actually lie on the line, and therefore it is a description of a straight line. And we call that a straight line written in parametric form because t is called the parameter. So this is called the standard parametric form for a straight line. And OP is the vector with coordinates x over y. And remember, OP is the vector that starts at O and ends at P, and point P has the coordinates x, y. Therefore, the vector OP has the coordinates x over y because it is the position vector for P. And this vector here, OP0, has the coordinates x0, y0 because it's a position vector to that point, x0, y0. And then I should say plus the parameter t multiplied by the direction vector. But the direction vector had the coordinates r1 over r2. And if I let t run through all the real numbers, then we describe all the points on the line Lone. There you have a straight line described in standard parametric form. Example. Let's say we have something that looks like this. X over y
Equals negative 1/3.
plus t times 1 over 2. And t should traverse all real numbers. And then we ask our neighbor, dear mathematician, what is this? And then the neighbor answers, hopefully, if he's a mathematician, that is a straight line passing through the point with coordinates 1, -3. And it is parallel to the vector here with coordinates 1, 2, because this is a direction vector for the line. If I am to draw this straight line, I start by plotting that point. Then I draw that vector, and then there is only one possibility. Let's try it. So I start by drawing that point. 1, -3, 1, -3. Let's say that -3 is here, and here's 1. So it lies here. And of course, there are infinitely many lanes that pass through that point, but we're looking for the lane that is also parallel to this vector. So I go 1 out and 2 up. And how many straight lines are there now that pass through that point, which are parallel to that vector? Only one, and that is the one we are talking about here. So this is now lone. And lone stretches infinitely in both directions. And this here was the vector r vector, which is my direction vector.
And especially this form, which we use to understand similar algebra.
As we begin to give it to them. Are there any questions? It's what is called the standard parametric form of a straight line. It is written in a form that involves a parameter t. It is called a free parameter. It can be whatever it wants. And every time it chooses to be something, you get a corresponding point on the line. I am taking a break. We'll just take 10 minutes until past. Then we'll continue with the story of the planes equation. And then we will get on with the syllabus.
in this new topic called linear algebra.
So if Alexander could pause, or Nora could pause the recording. Okay, let's continue.
The camera's rolling, and now we're going to take a look at it.
And the plan's direction. And luckily, it's a story very similar to what we've just done. Our new headline is the equation of the plane. And this is also something we will need to understand algebra for, because some of the solutions to our similar systems of equations result in the equation for a plane. And it can either be a plane in 3 dimensions, or it can also be a plane in 4 or 10. This just sounded like a hyperplane. But we need to understand the plane equation. And to do that, we need to imagine that we have a plane. So here is the plane. And you always just draw a part of the plane. But you should imagine that it extends to both sides. And let's say we have a point here. This point does not move, and I call it P0. And since we are in space, P0 has 3 coordinates: y0, x0, y0, and 0. We can also imagine that besides having a point P0, we have a vector that starts from P0, and that's our normal vector. So the plane is perpendicular to that vector. When that vector ends at P0, it has 3 coordinates, which we'll call A, B, and C. When I say it is a normal vector to the plane, you need to understand that it is perpendicular to the plane in 2 directions. So it needs to be 90 degrees here if you put a protractor on it, but it also needs to be 90 degrees here. So it is perpendicular in 2 planes, meaning that if this table here needed a normal vector, it should stand up like this, and it should be 90 degrees both here on one side and here on the other. So it has to be perpendicular in 2 directions for it to be a normal vector. So let's say I pick a point blindly, and I am so incredibly lucky that it hits the plane, and I call that point P. And point P is 3-dimensional, so it does not.
And now he has dealt the cards. And then I ask myself the question, what does it mean that P actually lies in the plan?
And it can be done in exactly the same way as with a straight line. I just create a vector from P0 out to P. There you go. If the vector is perpendicular to the normal vector, then P lays in the plane. But imagine that point P is not on the plane. But for instance, down here, then a vector from P0 down to P would not be perpendicular at all. And that's why I can use it as a condition to write the equation for the plane. Service.
And only if, then if.
Show P lies in the plane. I might need to name the plane so I don't have to keep describing it. I'll just call it alpha. That is the name of the plane now. So if point P lies in alpha, then I'm guessing the vector from P. It will be perpendicular to the normal vector of the plane.
And this, as we know, means the same
Of the dot product between the P0P vector
And the normal vector, it should give 0.
Because if 2 vectors dot each other and the result is 0, then they are perpendicular to each other. And if 2 vectors are perpendicular to each other, then their dot product is 0. And that was not the same thing I said twice. But it plays both ways. So this is called the equation of a plane. And you can see that it has exactly the same mathematical structures
Like the
as
equation
a straight line.
So this also applies in 10 dimensions.
This is also the line for a hyperplane. You really cannot see what the dimension number is here. You need to look up here and see how many coordinates the normal vector has. And if you just create the vector from P0 to P, we can just do that. How does it look? We have the vector that starts at P0 and ends at P.
Here we have some cardinal chains, they're called.
6.
Bonix.
The endpoint's coordinates. And then I subtract the starting point's coordinates. X0, Y0, Z0. And now I can form this dot product, set it equal to 0, and then I have the equation for the plane. So I'm just trying to calculate that dot product. What does it give? Yeah, P0P vector. The cross with the normal vector will give this vector x, y, z, x0, 0, 0. Multiplied by this vector called A over B over C. And it will then give first coordinate times, first coordinate plus second coordinate times, second coordinate plus third coordinate times, third coordinate. So it gives it over B over C.
X minus x0.
Plus
EY minus E0.
and plus C, Z0. Equal to 0. And the last one is the one that stands here. We call that the equation of a plane. It is the equation for a plane. And which plane is this the equation for? That is the equation for the unique plane that passes through the point in space with coordinates x0, y0, 0, and which has a known normal vector with the coordinates A over B over C. That part is it. Here is an example. If one day you come across something that looks like this,
Minus 2 times x plus 1.
plus 5 times we minus 3.
Minus 6 gang z plus 2.
Equal to 0.
And someone asks what it is. You should be able to recognize the structure of this, that it resembles that structure. Mathematics is really a lot about pattern recognition. And look at that. That's the equation for a plane. Which plane? Yes, that is the equation for the unique plane that has a normal vector with the coordinates. Then you read there, there, and there. So that means minus 2, 5, minus 6. Those are the coordinates. So it has this standard switch, the flat one. And now you have to be a bit careful, because now you need to find a point. You know the plane goes through. Is there a point we can read off that is contained within the plane? All right, x0, y0, z0 were the coordinates of a known point in the plane. And remember, you need to read after the minus. What comes after the minus here? After the minus that's not there, it's minus 1, because minus minus 1 is plus 1. So remember, if you see a minus, you're happy. If you see a plus, you're almost just as happy. You just need to remember to write the sign.
1 is always happy when checking paint.
So minus 1, 3, and here minus 2.
Minus 2, and you should read after the minus.
So what we're dealing with up here is the equation of a plane, specifically the plane that goes through that point and is perpendicular to that vector.
And here comes a tricky question.
Imagine now that a student is at a monthly math exam, and then the examiner goes up to the board, and then he writes, "Could you just tell me what this is?" What do you think? Are we trying to find a value? Then you recognize the same mathematical structure as up here. Okay.
A is 0. Then all that disappeared. B is 0.
0. Then all that disappears. C is 1.
And Z0 is 0.
What are you saying?
So we stand hidden here in front with a number like the CDs that have been multiplied on set.
That means this is the equation for a plane. Which plane is it? It's the plane that has the normal vector with the coordinates 0 and 0 over the E. What's that vector called? 0, 1? It's K. It's the unit vector K. We'll just do it like this so we can recognize it. And can we identify a point that we know this plane contains? Yes. 0, 0, 0. So it goes through the origin. So I have a known point
Here it should say 0, 0, 0. What is the plane that passes through the origin, which is perpendicular to the unit vector in the z direction? Well, it's not the seabed plane. That means I'm drawing it. Here is x, here is y, here is z, here is my normal vector, which is k. How many planes exist that are perpendicular to k? Infinitely many, but only one of them goes through the origin. And which one is that? It's this one down here. It's the xy plane here. The xy plane is called. So it's a really tough question to ask students during the exam, because that's the equation from the xy plane. And it's so easy, that task, that it becomes difficult. Because it's all 0. So that is the equation from the xy plane. And of course, it's nice to know that, especially if you're being asked about it. Let's see if anyone has any questions here. For example, drawing this here. I probably could do it, but it would take me about 10 minutes. Because I have to start by drawing this point in space. Then I have to draw the vector in space. And then I need to imagine how the plane is rotated. And it's not an easy drawing to make. So it's not that I don't want to. It's just that I know it's hard. And I also know there's a camera recording at the same time. So it's a sure way to make a fool of myself in public if I try to draw that one, I think.
No, like one of those that's hard to draw.
So you should not. You can easily draw it in Mabel or another computer program. It can draw it just like nothing, but it is difficult to draw by hand. Another thing is if it happened to go well by sheer luck, I believe it's intended for you to be able to do it as well, and currently you cannot. That's where you're supposed to use a computer program. Any other questions? So let's get started with some curriculum content. Now we're getting into the actual curriculum for the engineering program, which involves systems of equations. So if your pencil was not sharpened before, it needs to be sharpened now, because we are going to start with something you actually need to know. Not this was just a review of something you've already had. Let's do Saturday then. The easiest way to start understanding linear equations is to begin with an example taken from the real world. That way you can immediately get a sense of what it's about. So I'll start with an example, and the headline is, we are working on linear equations now, and we will start with an example. You walk into a store and buy a bottle and a cork. The bottle and the cork together cost 5 kroner, but the bottle costs 4 or 5 kroner more than the cork. We do not know how much the cork costs. We do not know how much the bottle costs. Together they cost 5 kroner, and the liquid in the bottle costs 4.5 kroner more than the cork. Welcome back. And your body feels like saying 50 cents, and that is wrong. So let's figure it out. So you go into a store and buy a bottle and a cap. The bottle and the cap together cost 5 kroner, which creates an equation like this. The cost of the bottle plus the cost of the cap equals 5 kroner. That's equation 1. But the bottle costs 4.5 kroner more than the cork. So take the cost of the cork, add 4.5, and you get the cost of the bottle. Equation number 2. And this is an example of a system of linear equations. And what does it mean that the equations are linear? That means the price of the bottle is not squared. It doesn't say the price of the bottle to the 8th power. It doesn't say the sine of the bottle's price. The only thing that has happened with the bottle's price and the stopper's price in that equation, and the only thing that has happened with the bottle's price and the stopper's price in that equation, is that the two unknowns are multiplied by constants and added together. And that is the only thing that has happened.
Maybe if it needs similar alignment.
So the unknowns can be multiplied by constants. The constants can be positive, negative, or 0. Then it should be put together, and then there should be constants on the other side.
That's cool.
So if you want to write this equation in standard form,
It's really simple because it's already in standard form where it says 1f plus 1p equals 5. But this one here is not in standard form. I want the constant over there and the bottle's price over here, so I'll just rewrite equation 2. So it will say the cork's price minus the bottle's price.
That makes negative 4.5.
And now you can see that it says 1p minus 1f should equal a number. And now they say that you have written the two equations in standard form. So this is still equation 2, just written in standard form.
So how do you solve such a system of ideas?
This part of the course is about a method to solve systems of equations, no matter how many unknowns there are. So we can solve n equations with n unknowns. But right now it's just two equations. Fortunately, with only two unknowns, so we have an easy start. So let's try to solve it. The first thing I could do is isolate f in equation 1 and substitute it into f's position in equation 2. You learned that method in elementary school and in the first year of high school, so you can see that it definitely works. So I'll just take line 1 and then I'll add f. If I isolate f in equation 1, it should give 5 minus p. So what you are saying is that you now have found an expression for the bottle's price. And that expression can be substituted for the bottle's price in equation 2. So now I substitute equation 1 into equation 2. So if I insert equation 1 and work on equation 2, then it says p minus f, but f was this, right? And remember, you need to use parentheses because f contains two terms.
So here stands f in disguise, and it should be that with 4.5.
And what I've gotten out of this now is one equation with only one unknown. This means I can now find the price of the cork and answer the riddle. So what I do is remove the negative parentheses and get p minus 5 plus p.
They are with minus 4.5.
So I'm just counting how many p's I have, 2p minus 5. But I move the minus 5 to the other side by adding 5 to both sides of the equation, so I get 2p.
Along with 4.5. Plus 5. There we go.
What does it say then? You have 5, you eat 4.5.
There you have a whole one.
What's the gentleman doing standing there? 0.5 written in physicist language, 1/2 written in mathematician language. So 2p should give half, but then I can find p. I just need to divide by 2. So the cork costs,
It's a quarter crown.
And that's the same as
25 with the Danish way of counting money. Does that make sense? You go into a store and you buy a bottle and a cap. Together they cost 5 kroner. The bottle costs 4.5 kroner more than the cap. How much does the cap cost? Well, if the cap costs 25 øre, what is 4.5 more than 25 øre? It's 4.75, and 4.75 plus 25 øre makes 5 kroner.
when the money is right. The cork costs 25,000 kroner.
So now that you have found the unit price, you can find the bottle price just by going back to it.
The place where I isolated the bottle's price.
And the bottle's price.
It was 5 minus the price of the cork.
That means it is 5 minus 1/4 if we write it in mathematical terms. And here there are 20 quarters, so if I take away 1/4, I'm left with 19 quarters. So a mathematician would say that the cork costs 19 quarters, but the physicist will quickly convert this to 4.75. Because if you need to pay a cashier for the rent, you just have to tell
Here
her.
is 19 quarters on the bottle.
They have a hard time assembling the whole roof down in the box, I've noticed.
Let's try to make a mess of things.
Yes, so this is an example of two equations with two unknowns that I came up with here.
Oh, well, these are two equations.
Math. Hard to get to know. Any questions about it? Your turn. Preben and Benny are out fishing. Here's the task for you now, and then we'll pause the camera when I've written it down so you can try to call it.
So task now.
Caught it, yeah. Oh, Benny. Of course. Caught several fish. So Preben and Benny went fishing, and they each caught a number of fish. We know Preben caught more than Benny. So I'll then start by writing P greater than B. This means that Preben has caught the most. And since Preben has caught more than Benny, if Preben gives one to Benny, they have the same amount now. So I'll just write this down. If Preben gives Benny fish, they have the same number of fish. Gives Benny one fish, they have the same number of fish. So if Preben gives Benny a fish, then they have the same amount. If, on the other hand, Benny throws a party for Preben, then Preben has twice as many as Benny. Then we have use against. I just can't feel that it's a fish. So, hit twice as many as Benny. And you need to figure out how many fish you have caught. To start with, go on then. Find P, which is the number of fish Preben has caught, and find B, which is the number of fish Benny has caught. Go ahead, try to solve it. I'll walk around and help if anyone needs assistance. We'll take the task to the board. First, I'll show you how to do it if you've only gone to high school or elementary school. And afterwards, I'll show you how to do it.
Only do it if you
Get started with it. It needs to
We're
be done.
approaching algebra.
And this is the first topic we will have under equations and algebra. But let's solve it first without any knowledge beyond elementary school math, actually. So what it says over here is that Preben and Benny have each caught a certain number.
Selfish. Just
Notice
put one
that if I use P, so P means the number of fish he starts with
Has caught.
before he begins to gain or lose any.
P and B refer to the number of fish Benny has caught. And so if Preben gives Benny a fish, then they have the same amount. So it can be written like this in equation 1. If Preben gives one away, he will have one less than he originally caught. So he will be down to having P minus 1. And it says that it's the same number that Benny has now after receiving one. And when Benny has received one, he obviously has B minus 1. So that is the first equation. What it says here, written in math, is that if Preben gives a fish to Benny, then this number is just as large as that number. Yeah, because that number represents how many fish Benny now has after receiving one. And that represents how many fish Preben has after giving one away. And there it says they have the same amount. What's challenging in this task is translating the language into equations.
And that is something we do not practice as much anymore.
Now comes the next one.
If Benny, on the other hand, gives away prizes,
Fish, then Preben has twice as many as Benny.
So the first thing to write down is
we are taking one away from Benny.
A number that is one less than what he has caught. And then we know that the Draben has one more than he has caught now. But what the text says is that afterward, Preben has twice as many. This here is how many Preben currently has. And this is how many Benny has now. And we know that what Preben has now is twice as much as what Benny has. So that means if I multiply here by 2, then it should give that result.
In Danish, it says that if you take double, you're ready.
That is the number of fish Benny has after he has given one away. That is how you find out how many fish Preben has now after receiving one. And this is the line that's a bit hard to set up if you're not used to thinking like this. To solve them, I can start with lane 1 and isolate P. So I'm isolating P up here. By adding 1 to the rear of the equal sign, I get this. That means another way to write P is B plus 2. So what we know now is that there are 2 fish in between. However many Benny ends up catching, Preben has caught 2 more. We already know that. So this expression for how many Preben has caught, I can insert it in Preben's spot there. So I substitute aligning 1 into 2.
It says there twice.
B1, just like before, should be equal to P minus 1, but instead of P, I write B2. So B minus 2 plus 1, here P is in disguise. And form an equation with only one unknown, and then it can be solved. So if I multiply into the parentheses, I get 2B minus 2. And on the terror, it says B plus 3.
I can add 2 more to the back of the guiding sign.
Then it will say 2b right here with b plus 5.
And then I can subtract B from both sides of the equation.
And 2b, 1b, db.
So Benny has apparently caught 5 fish.
But I also know that Preben has caught 2 more than that, so he's caught 7.
The number is 7. We can see that right away because we had already found that equation.
So the answer is 5 and 7. And now you can see that if the one with 7 takes one of his fish and gives it to the one who caught 5, then they both have had 6 fish. 6 fish, that was hard to say, not fish. And if the one with 5 gives one to the one who caught 7, then he now only has 4, but he has 8. So now he has twice as many as the other one. So the fish fit into this task.
Any questions?
So let's evaluate the assignment. Let me show you how you could have solved it using another method, which turns out to be much, much better when there are many unknowns and many equations. And to understand it, you first need to grasp what I'm about to explain over here. Did I forget to call it the blackboard? Do you remember that?
We'll define it a bit later.
Let's just understand something about equations. Look, if it says like this.
For example, 3. If it says like this.
2x
plus 3y, then I have to give 8.
It was aligning 1 and aligning 2.
Minus x, among others.
Speak any.
You cannot just look at it and say what's x and what's y. I can't, at least. And if there's anyone who can, just by looking at it and telling what it is, then I don't think they need to take the course. But then there's no reason to let them run a shop if they can just see that right away. It's not that easy to see just like that. So this is an example where 2 equations with 2 unknowns are not together.
Radiates the answer right in your face. But sometimes you get 2 equations with 2 unknowns.
Where's the answer? Try looking at that example.
Example 4. If it says something like this, 1x plus 0y, should I go all out? And in row 2, it says 0x plus 1y has to equal 8. Here there are 2 lines with 2 variables, but the answers are also written. Because what does 1x plus 0y give? It just gives 1x. And what is 1x? It is x. So what does it say in line 1? X is 5.
And what does it say down in line 2? Y and A. Can you see it?
So the difference between this system of linear equations and this one is that it's much better to get one like this, because then you can just give the answers right away.
So imagine if there was a really clever way to go from that line system to this one, like this.
If that method existed, it would be super cool, because then you could go from a system of equations you couldn't figure out to having the solution appear right away. And there is such a method. Gauss came up with it, and someone named Jordan contributed a bit, so it is called the Gauss-Jordan method. And we call it Gauss-Jordan elimination And now we need to learn that method. It's super cool to get it down. I get chills just thinking about it. I mean, it's pretty wild that someone figured this out, especially since it has all kinds of geometric meanings that we will discover along the way. You can imagine what's happening in space. There are all sorts of things happening in space.
While you're actually doing them.
Well,
But in any
let
case,
me tell you about this method, and you'll discover something with me. Namely, if you look at these two equations with two unknowns, the only important things are the numbers 2, 3, 8, minus 1, 5, and 9. So if the only things you are allowed to do in equations is multiply by numbers and add them together, then all the information about the system of equations must be contained in the numbers 2, 3, 8, negative 1, 5, 9. So you simply write all the numbers into a box, and that is called the matrix. So you make a matrix that looks like this.
minus 1.
That burr means you come from the right side.
And now,
That matrix over
As
there,
they call it here, it contains everything.
it's called the total matrix for the conduction system because it contains all the information about the system. If you had made a matrix that only contained 2, 3, minus 1, 5, just this, it would be called a coefficient matrix, and I'll explain it again next time. Because then you take all the coefficients 2, 3, minus 1, 5 for the unknowns x and y.
So this is called a coefficient matrix.
That's the right side of the system of equations. And if you merge the right side with the coefficient matrix, you get what is called a total matrix, which contains all the information. Let's try to write our total matrix for this system of equations. Here's how it looks.
it says 10,500 then.
Here comes the right side 5.
Needle 1 here. Needle 1 here.
That there is also a total matrix just for a different system of equations. So this is also a total matrix. But the decisive difference between that overall matrix and this one is that if it looks like this, the solutions are right there.
Can you see? X was 5, Y was 4.
What
Why?
does it say here? 1x plus 0y equals 5. So x is 5. Here it says 0x plus 1y equals 8. Well, then y is 8. So the whole point is if I can come up with a method that magically transforms a total matrix that looks like this into a total matrix that looks like this, if I can just pull off some magic, then the solutions are right there. And this is what I'll magic up for you. I just want to show you with the task with Preben and Benny. So here comes the example. And I will simply show you the method, and later you will understand why it worked. I'll just show you the method first. So what do my equations look like? Well, I had one here called p minus 1, which is b plus 1. I'm writing that equation again. So I write it like this. P minus b is equal to p minus b, 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 p minus b. Do you agree with me that this equation here, called p minus 1 equals b plus 1, is the same equation I'm writing up here? I basically just subtracted b from both sides and added 1 to both sides. And the reason I'm writing it like this is because now it says some number times Preben plus some number times Benny equals some number. So I have the mathematical structure that corresponds to the one up there. A number times x plus a number times y should equal a right side. A number times an unknown plus a number times an unknown should give a right side.
So that's the one line. Then I'll take the other line that says,
Oh, yeah.
And I write it as 2b minus p.
2b minus p.
Anyway, that gives minus 2. It moves over to 3. So it should say 3 over here. Did you get that?
So 2b minus 2.
Minus 2, I move over to the 1 from 3 and I subtract p, so I get 2b minus p. Dang! Here is a system of linear equations. Now I write down the augmented matrix for this system of linear equations. It looks like this.
1 minus 1, 2.
1, 1, 2, 1's like that, right? And here it's supposed to say 2 and 3. Did I do it right? Let's take a look.
Tighten it properly.
That's exactly right. So I take this equation up here, and then I've moved b over here. So it says p minus b, and that number over there is equal to 2. So p minus b equals 2. That was one equation. There was the second equation that was here. I moved p over here, so it says 2b minus p.
It's minus 2, add 1, that makes 3.
Oh, yeah, you're right. Sorry. I should write the p's under the b's. Or the p's under the p's and the b's under the b's. You're right.
That's completely right, what you're saying. So it should say B.
So who's 2b?
Like that, right? Minus p plus 2b and 3. Yes, now it's correct. It's correct because just like I wrote x under x and y under y here, to find the coefficients, they need to be aligned like this. And that's what I had just gotten mixed up about. Are you following? Okay.
So now it says 1 minus 1 minus 1.
And here the dotted line continues and then pull. And that is my total matrix. Now I am satisfied with it.
Now you can
do something
then...
super clever. This is what you call a row. And this is also called a row. This is called row 1, and this is called row 2. Now we do what is called row operations. And what you're trying to achieve with these row operations is to have ones on the diagonal and zeros outside the diagonal. This is called the diagonal, and this is called outside the diagonal. Because if you can get ones on the diagonal and zeros outside it, then the solution is right over here. And this form is called reduced row echelon form. In English, in Danish, we call it a trapezoidal form. But we are trying to get a triangular form because there's this sort of triangular form here, you know, where there are ones on the diagonal and zeros outside the diagonal. And that means if we look at the one I have here, we are already pleased with that one because it's a one that already stands on the diagonal. So the question is, what can you do with these rows? What's allowed? And what you can do is add two rows together. You can do it. You can also do it with equations. You can add two equations together. Because is it not true that if 2 equals 2 and 4 equals 4, then it is certainly true. So it is still true that if I add the two together, it is also true if the two are added together, even if I have changed the order here. So if you have two equations, both of which are true, then the two combined equations will also create a new equation that is true. So I can take this row and add it to that row. So what I do here in row 2 is I write something new, which is the old row 2 plus the old row 1. And the symbol here means that you now get a new coefficient matrix that corresponds to a system of equations with the same solution. So it is not an equal sign. This means that this total matrix is equivalent to this one, understood in such a way that it corresponds to an equation system with the same solution. And if I add them together, what do I get? Minus 1 plus 1. It is 0.
Minus 1 plus 2. It is not 2 plus 3.
That's cool. And up in the top one, I haven't done anything. So that copy paste is the top row 1, minus 1 and 2. Were you following that? So what's written here is an instruction for the reader that says what he's done is taken row 2 and added it to row 1. And whatever he gets, that becomes his new row 2. So my new row 2 is the old row 2 plus row 1. And this plus this equals 0. That's why it says 0. This plus this equals 1. That's why it says 1. This plus this equals 5. That's why it says 5. I'm with you on that. Now we can see that we are getting a bit closer to having our reduced row echelon form. Because now we have a 1 there, but we also have a 1 there. And we even have a 0 there. So the only thing we need is to get a 0.
And we just do the clever thing of adding row 2 to row 1. So now I replace the old row 1 with row 1 plus row 2.
And what will it say then? This plus this.
On, and on.
It is 0. That plus that.
That's funny. And down here I have not done anything, so I will copy paste that 0, 1, 5. And now it's done. Now there is a number in the diagonal and zeros outside the diagonal, so I have achieved a complete matrix in reduced row, echelon form, ladder form in Danish, and here are the solutions. So one person has caught 5 fish and the other has caught 5 fish. Super clever. Does anyone have questions about the story?
Mats?
It's because the part at the end is what's on standby. Remember 0B. It says 0 here. Teams what Preben caught plus what Benny caught is 5 so soon.
You have a 1 Euler's zeros.
When there are ones on the diagonal and zeros outside the diagonal, the system of equations is solved. And then there's a solution like on the right side over here. And that is what is so insanely clever. Let's just take a 5-minute break. I know we have until 12:30. 11:50, let's take a 5-minute break and then we'll continue because I can feel that I need some kind of sugar. Let's just take a quick break. Okay, let's just take a look at what it is we have actually done with a geometric interpretation. So we erase everything. And then let's pretend the story starts over. Preben and Benny went out fishing. Preben caught more than Benny. If Preben gives Benny 1, they will have the same amount. If Benny gives Preben 1, Preben will have double what Benny has. How many have they caught? What does that mean for the 12th geometric sequence? That is the question now. If we start from the beginning, we say that if Preben gives 1 to Benny, then Preben has twice as many as Benny. So Benny has 1 more than he had before. Preben has 1 less than he had before, but now it's the same amount. Equation 2. During tension, I yield inward. Then you get a number which, if you multiply it by 2, gives you exactly as many fish as Preben now has after he has received 1. So it's 2 equations with 2 variables. We're now going to write them in standard form, but not the standard form I showed before, rather the one my neighbor understands when he thinks of straight lines. And how did it look again? Oh yes, a straight line was x plus by plus c equals 0. Do you remember if I asked my neighbor, what is this? He would say, this is the line for a straight line. Which straight line is it? It is the straight line that goes through a point I cannot quite see, but it definitely has the normal vector with coordinates a over b. So I will now rewrite both lines in these structures. This is what line 1 looks like. But then when she boosts, the order store, hi. Then I subtract b over here. Then it becomes minus b. And then there is minus 1 here. So I also subtract that one number, making it minus 2. And then on the right side, it equals 0. Can you see? I want 0 on the right side. Were you following that? So in reality, it says 1p minus 1b minus 2 equals 0. Let's take equation 2 and do the same. What does it say here? It says 2b. We multiply that out. So it says minus p, like that. And then there is plus 2b when I multiply inside the parentheses. And the minus 2s becomes minus 3 when I subtract 1. It works nicely. 2b minus 2 -3 in -4.
And then I ask my buddy what this is, and he says it's a pretty small idiom. It is a straight line drawn in a coordinate system with a b-axis and a p-axis. So let's say this is x and this is y, right? That would correspond to the x-axis, and that would correspond to the y-axis. Now I want to draw the two straight lines. So on this straight line up here, I'll just find a point, PO. And I don't know if you remember how to do it, but you just pick one of the two variables yourself. Let's just say we set b to 0. Then you can see that p minus 2 must be 0. And then p must be 2, right? So p is 2 when b is 0. So that is the point. We know the straight line goes through. And down here, we can do something similar. We can set b to 0, and then we can see that p has to be -3.
Because -3 is +3. -3 is 0.
So what did I conclude? Over here, it was at least 0, and then I said -3. So p should be -3. Do you agree? If I put -3 in there, -3, that's +3. +3 minus 3, that's 0. And b was 0, so it all adds up to 0. So now I know I can draw the two straight lines there. So now it comes geometrically, so we can see what it is we are finding. I better make a little effort so the drawing makes sense.
P-axis and a B-axis.
Then there is a Preben axis and a Benny axis. Then I need to draw this straight line here, passing through the point 2, 0. Let's say it's 2.0. It is there. And then it has a normal vector, this straight line called 1, -1. Isn't that right? That's its normal vector.
You should just write to us here.
1 has the normal vector n with coordinates 1, -1, -1. And in 2, I see that it has a normal vector, so it's called -1, 2. -1 and 2. So now I can go over and draw the two straight lines. So the first straight line here, it should be normal weight. So it goes one to the right and one down. From that point, it goes one to the right and one down. So it looks roughly like this. And that means one line must look like this. You should be perpendicular, of course. Now I need to draw this line. I have to plot the point, 3 Daru. -1, 2, -3, it's here. So it needs to pass through this point here. And its normal vector goes 1 to the left and 2 up, -1 and then 2 up. So it looks approximately like this. And this is the straight line that passes through it. It is right here. And if I can also draw it somewhat accurately, the two straight lines intersect each other instead. And if my drawing is somewhat reasonable, then it should say 7 here, because that's how many bream they caught. And here, do you see it? So you can see that what we have actually found is the intersection points between two straight lines in two-dimensional space. That is the geometric interpretation of a linear system. We have found the intersection between two straight lines, and at the point where they intersect, it shows how many fish they have caught. So there is a connection between reality and geometry. And it's not just in this situation that there's a connection between reality and geometry. Perhaps the entire reality is pure
Geometry. That's what I suspected.
And I'm mentioning it, of course, because Einstein did. Because when he invented the general theory of relativity, he got the idea that maybe the moon does not move in a circle around the Earth, but in a straight line in a curved space, where space curves due to the presence of the Earth. But it turns out you can interpret it in another way geometrically, not just as an intersection between two straight lines, but like what's coming in the last 5 minutes. So let's take another look at what is actually being stated in these two equations here. What is actually written there? There's P times a weight, isn't that right? Look here, EP multiplied by a weight, and B multiplied by a weight. Then I can look into the weight. Let's see if you understand what I'm saying here. What is P multiplied by for a vector?
it is a 1 and a minus 1.
1 minus 1.
Minus 1, 2. And what vector is on the right side? Well, if we add 2 and 3 over there, then it just says 2 and 3. If I move the 2 over there and move the 3 over there, just look at what it says. D times the vector. Should I give that vector? How do you multiply a number by a vector? Well, you multiply up on the first coordinate and multiply down on the second coordinate. You multiply up on the first coordinate and multiply down on the second coordinate. So what it actually says is 1p plus minus 1b should equal 2. Oh, that's also what it said here. 1p minus 1b equals 2. But the thing with this is that it cannot be interpreted geometrically. And here it says that you know one vector and you know another vector, and you combine them to get that vector. It gives me a sad question. If you multiply a vector by a number p, what happens to the vector? You make it longer if p is greater than 1. Remember? You make it shorter if p is between 0 and 1.
It shifts
Correct
under
thing,
tension.
negative. So what it's really saying here is that you have one vector and you have another vector. Can you form this vector? So if we imagine that this was the vector, which it is not, but if it were, and that was the vector, what this line is essentially saying is, can you combine the two vectors by multiplying with suitable scaling constants, p and b, to form that vector? So the story of Preben and Benny can be interpreted as having one vector and another vector. Can you stretch, compress, or flip that vector? And by stretching, compressing, or rotating it 180 degrees, combine them to get the desired result? If you can, then you have found the right scaling constants, which represent how many fish they have caught. So it is a new geometric interpretation. So linear systems of equations can be thought of either as the intersection of straight lines, if it's two lines with two unknowns, or as scaling vectors with scaling constants to get a third vector. And this is called forming a linear combination of two vectors to obtain a third. And we will definitely come back to that. Next time, enjoy your lunch. Thanks for today.